Hi, everyone. Welcome to Automated Embedding in Vector Search. We're going to talk about how the landscape has changed for search and AI-native applications, and what role MongoDB is playing with the launch today. So just to get started, I'm Prakul. I'm a product manager here at MongoDB, and joining me will be my colleague, James, who is on the engineering side of things. So let's start with how AI has transformed search. So at the very core, we have seen search becoming not about keywords, but about the user intent. Just in the short while, users have been trained to put out the actual question they have, which is replete with relationships, semantics, and get a rich result back. Now, on the left, what you see is the old world of search, where you ask a specific keyword-based question, Q2 sales results. You get those narrow result set, which are documents which match those keywords. On the right is a new world of search, which is user asking a question, how did revenue trend in Spain, right? Which is exactly what they mean. And the expectation is to get back this rich, relevant results, which are pertaining to that search query, could contain the May forecast, could contain April financial summary, etc. And this AI-powered search has essentially been powering transformative use cases. A lot of you here would be building a lot of these applications, but we have been seeing a lot of usage of semantic search, which is search based on user intent. This is what powers intelligent search interface on e-commerce websites, for instance. There is RAG, or Retrieval Augmented Generation for large language models, which lets you ground your responses in the proprietary data. This is how your co-pilots, intelligent assistants, and chatbots are powered. There has also been an implosion of applications leveraging AI agent memory, which lets an agent build context using the long-term memory store. So this search, AI-powered search in the old way, has been built in the following way, right? So it's a two-tower approach. There's an indexing step, there's a querying step. So in the indexing, you take all your data source, the knowledge corpus on which you want to enable search, pass it into indexing pipeline, which will involve doing a lot of data processing, having some orchestration for talking to the embedding models, reaching out to that embedding model as its own, and that's when you're prepared, you will store it into a database and a vector search, right? With a lot of you in the room are aware, MongoDB has a native vector search integrated into the database itself. So that indexing flow exists, and then on the querying side, you would take a user query, convert it into an embedding, and that's how you get your search results. So this workflow was already simplified by MongoDB by having a single place where your database, your transactional database, and your vector search is. But we have been hearing from our users all sorts of pains. Like, this setup exists, but this can be brittle, this can be error-prone, this can be fragile. So just to lay out a few of the common challenges that we have been hearing in terms of building this AI-powered search. So firstly, there's a steep learning curve. Getting started can be a pain for teams new to embeddings, machine learning. There is, secondly, the integration complexity. So every time you insert a document, you have to reach out and talk to an external embedding model endpoint in your application code, which involves all sorts of retries, authentication, payload management, etc. Thirdly, there's a synchronization challenge. As you saw all the moving pieces, your data, your embedding, and what's in your vector search, all of that needs to stay in sync. Having stale embeddings will lead to bad results. And fourthly, there's a production scale headache. Making a embedding model call could be a trivial thing if you have few documents, but when you're looking at millions of documents, this becomes a nightmare. You're essentially looking at building task queues for handling those data. You are building retry mechanisms. You're building specialized workers. You will need some kind of alerts and monitoring that makes sure the entire process of embedding generation is happening and is not going into errors. Also, your database operation cannot get blocked by the slow process of embedding generation, because these are two different paths that takes. So you don't want your database to be blocked by embedding generation that's happening. So that is what brings us to automated embedding in vector search. With automated embedding, our goal was simple: to make it not a developer's concern to generate these and manage these embeddings in their application code. Let the database handle all of those operations. You, as a developer, should be able to focus on building differentiated applications and not dealing with all the infrastructure challenges which comes with place. So the solution for that is the introduction of our automated embedding search index. A lot of you are aware, MongoDB has had lexical search, full text search, as well as vector search. And the way these search works are via these secondary search indexes, which are defined as search index or vector search index. So the auto-embedding search index is a subtype of vector search that we're releasing right now. You just define a type equal to vector search. You define your type equal to auto-embed as a type, define modality, choose a model. A lot of you are aware, MongoDB has the acquired company called Voyage, which makes state-of-the-art embedding models. And you define the path. This is your path in your MongoDB document on which you want to enable semantic search on. This could also be a view where you can define that in your document, these are the fields I want to make a composite, and that's what I want my semantic search to be on. But with this index definition, you are good to go, and your process of embedding generation starts. Similarly, similar approach on the query side. When you do a query with auto-embedding, all you need to do is use the MongoDB's operator $vector search. It's an MQL stage. We are introducing new parameters for query, where you're passing the text, the natural language text that you want to do a search on, and you provided the model that you want to use for embedding. So this is an optional parameter. I think some of you would have seen we released new class of embedding models, which have some special capabilities. So you can switch the model at the query time and indexing time. We'll talk more about it. But with that, you're good to go. This becomes your semantic search setup. Like this allows you to build those AI-powered search on your data. So with auto-embedding, this is where we get to. Put your data in to MongoDB, define a search index, and you're good to go. You're running a query. So data in, data out in that one-step process. To get started on this, right, like we are releasing auto-embedding in public preview on MongoDB community. As you're aware, MongoDB community is a self-managed deployment that you can run on your local system. To do this, you essentially need three things. One is the MongoD, which is the database daemon, which is available in a Docker image, as a Linux binary, etc. We had released this thing called MongoT, which is our search daemon. Right? This was released a few months back. Today, we are open sourcing this as well. You need this, again, similarly available as a Docker, as a Linux, and you need your Voyage model API key. So this Voyage model API key can be obtained on MongoDB Atlas itself. That's a new product we announced today. Or you can do this on voyageai.com. Get the API key, initialize that when you're setting it up, and you're essentially good to go. So this is a one-time setup. With that, we essentially get to this three things that enables you to do. One is this intuitive setup. Define an index, and MongoDB handles the rest. All the infrastructure challenges are something handled by us. Secondly, radically simplify your architecture. Just write the raw text to MongoDB in that high throughput, low latency manner, and the search index will get generated in eventually consistent manner. Your writes are not blocked. You get quick performance, and your embeddings, which can be a slow process with all the resources required, will happen eventually as we wait for it. Thirdly, there's complete automation. You continue updating your documents, writing more documents, deleting it. Your embeddings and your search index is always up to date. Now, at the very core, these are powered by state-of-the-art Voyage models. Voyage models, and we release these models today itself. Auto-embedding comes with day zero support for these new models. But these are, the reason I call them state-of-the-art is this benchmarking score that I have, the graph that I have on the screen. So again, these are industry benchmarks using the RTEB, Retrieval Text Embedding Benchmark leaderboard. But on that board is where these results coming from. So the Voyage 4 large model is a flagship model that we release. This is the first production grade application, the embedding model to use a mixture of experts architecture. This outperforms OpenAI's V3 large embedding model by an average of 14%. Next up, Cohere V4 Voyage 4 large is better than that by average of 8%. And Google Gemini embedding 01, which is the latest embedding model from Google, Voyage 4 large outperforms that by 4 percentage point on this leaderboard. So auto embedding comes with these models, and there's also Voyage Code 3 model, which is specially trained for code searches. So if you had those, you can use it. But within these models, you have option to either get the maximum accuracy with Voyage 4 large. With Voyage 4, it's a balanced of accuracy and latency, and 4 Lite lets you do high throughput, low latency application. Obviously, these models have different price points, and our system lets you make that choice. With that, let me bring on stage my colleagues. I talked about the why and the what. James will talk about how the solution works.
Great. Thanks, Prakul. Can folks hear me? Is my mic working? Okay, it also fell off of me, so bear with me a moment. All right, yeah, so as Prakul mentioned, auto-embedding is a feature that we're releasing that allows users to perform semantic search without needing to worry about vector representations and without needing to worry about keeping vector representations consistent with source documents. My name's James. I was one of the engineers on the project. And I want to take some time to talk about the technical challenges that we needed to address when implementing auto-embedding, and then walk through the solution that we came up with for those two towers that Prakul mentioned, that index time operation and the query time operation. This slide speaks to 3 of the technical challenges that we wanted to address. First and foremost, we wanted the auto-embedding system to be performant. What that means is low latency search results. We didn't want to introduce any unnecessary latency in the indexing or the query pipeline. Additionally, we wanted vector representations of source documents to be durable. Oh gosh, am I good? I think people, sorry. Additionally, I don't know where to stand. Is this good? All right. Additionally, we wanted vector representations to be durable and consistent. What this means is that vectors should persist as elements of a deployment are spun up and down, and vector representations should remain consistent with the source collection as the source collection changes. Sorry. It's all good. Finally, we wanted to reduce the network I/O across a deployment by deduplicating calls to the Voyage API service. What this ensures is that there is one call to the API service per document index, and per query. So I want to take some time now to walk through the system as it pertains to indexing. So here we kind of see several actors. There's the user here. Prakul also mentioned that there are multiple processes that run when search is deployed in community. There's MongoDB, which is the database instance represented by the disks. There's also this special process, MongoT, which handles search operations. If you're using auto-embedding and you have a replica set up, you will need to designate a leader MongoT that has some special responsibilities when building the index. Finally, we have the Voyage API endpoint, which is called by the search process. So when an index is defined, when an index is defined, that index definition is proxied through MongoDB to MongoT, and the leader MongoT picks up that index definition and performs a collection scan and monitors the change stream. During the collection scan, MongoT will batch documents that are to be indexed and call the embedding service for that batch. When the leader MongoT receives vector representations of the source documents, it will write those representations back to a reserved namespace in MongoD. Because we're using MongoD to persist vector representations, those vector representations will stick around, even as components are spun up and down within the system. Additionally, when the vectors are received from the embedding endpoint, they are put in to an underlying Lucene vector index. Lucene is a vector search engine that's used at MongoDB. It's highly performant for vector search. And when the vectors are written back to the search namespace, those writes can be picked up by other nodes in the replica set, and those vectors can then be put into any other MongoT's Lucene vector indexes. What this gives us is performance, because we're using Lucene as our underlying vector search engine. We have consistency and durability because we are persisting our vectors in. And finally, we're deduplicating calls to the embedding endpoint, since there's one MongoT that's responsible for reaching out to the embedding API. Next, I want to talk about searching and how that's handled. For searching, we now don't need to worry about a MongoT being a leader or a follower, because every MongoT will have a consistent view of the vector representations from the source collection. So a user starts by issuing a query. That query is proxied to the search node, MongoT. MongoT then can look within that query, extract the plain text, reach out to the embedding API, get the vector representation of that plain text, look at the underlying vector index, and return the document IDs that are the nearest neighbor to the query vector. It's important to note from this workflow, the user just sees a plain text query and gets a list of source documents from the source collection. So this whole notion of calling an embedding model and vector indexes is just hidden from the user. They interact with the system entirely with plain text. I'll hand it over to Prakul for a demo now.
Thank you, James. Can we switch over to the demo, please? All right, so I'm actually going to use a recorded demo. There have been some issues with Wi-Fi. So to get started, the first thing is I have the cluster set up, and this is the local host. So we just got the connection through an Compass. Now, this database, this is MongoDB with MongoDB running, comes with a few sample data sets. So for this purpose, we are going to be using a movies data set. These are 21,000 documents of movies, contains metadata about them, title, the plot, genre, etc. And think about the use case where you're talking to a friend, you want to tell them you watched a movie but don't remember the title, but you remember the plot and things that happen there. Or like you're trying to make a recommendation and just have a mood and you want to search for it. So that's what we're going to demonstrate today. So to build that out, first thing is we want to just on the plot be able to do a semantic search. To do that, we are going to go to indexes and create a search index. This can be done programmatically in tools like Compass, other ways. Create a vector search. Basically put in that index definition that I talked about. This is your type equal to auto embed. Choose a model that you care about and click on search index. As you kickstart that process, you will essentially see this status. So index is pending, building now, and if we continue focus, this is actually the real-time thing. It will take a bit of a time, 21,000 documents all being embedded with the Voyage 4 large model. But you can monitor, go away for this time. These are just 21,000 documents. It will happen soon, but if these were 100,000 documents, you are not babysitting this process. But a lot of the builders in your room would know what kind of pain it can be if there are millions of documents. But essentially, this will take a while. You can monitor the progress. And once that is ready, you will see it get into the ready state. So basically right here, once this index is ready, let me just make sure we capture that. Yeah, there we go. So you can see the index has now moved into the ready state. You can obviously monitor the progress, but once this is ready, let's run some queries. To run queries, you will be basically going in to your favorite query thing. This could be programmatic experience. Automated embedding also comes with day zero support in MongoDB's MCP server, in our LangChain integration, and a LangGraph integration, as well as language drivers like Java, Go, etc. So now the query I'm running here is really a vector search query. And the text I have here is a fairy tale where someone falls in love. So there is no model defined here. So the results that you see are on the left. I realize this may be a little blurry for anyone to see, so I'll read it out. But for that query, you essentially get the first result of Frosty, second is Stardust, third is reconstruction. Now, let's actually modify the query a little bit. So, and I modified my query to say, let me add a different model. So what I'm going to do is, this was using a default model, which was used during the indexing time. I can go ahead and add this model here, which is Voyage 4 Lite. Now you will see the results change in order. And changing that model is super straightforward. So a lot of you builders would have seen, iterating on this can be such a pain. So now, depending on your use case, do you care about the accuracy? Do you care about latency? You can make these changes in real time during the query time, right? Like the indexing stays the same. And this is a new innovation. We are the first model providers which have this capability in a commercial setting. Now, let's make the query more interesting. So right now, what I have is the model is Voyage 4, and the query is fairy tale where a monster falls in love and lives in a swamp. Now, for the movie enthusiasts, you would know this is a very popular movie, something called Shrek. So right now, we are searching that with Voyage 4. So the first result I'm getting right here is something called Swamp Thing, matches that description. The second one is the Tammy and Bachelor. The third query is Monster in Paris. So we actually see Shrek, but the Shrek is further down the list. It comes around the sixth result set. Now, what I want to do is change that model that I'm using at the query time back to Voyage 4 Large and see how the result changes. So now what happens is the first result I see here is the Shrek. So when we talk about the accuracy of the retrieval and how models impact that, this is that process in action. So your first result is Shrek, and you see other results. So these are all the things that make it easy. I know we are over time a little bit, so we're going to break for question, but you can do things like you see the original thing that we have, the object that we have on which we enable the search on, also had certain things like year, so 1982. So if you had a query, give me a fairy tale where monster falls in love, lives in a swamp, and the movie was released before 2000, builders among you will know, like, embedding models don't really work well on the dates, right? It works well on the natural language context, but the date part will be ignored. It won't do well. So you can actually create a pre-filter and define that in a MQL stage, definitively that like you need movies to be less than 2000. You can also do things like combine plot and title. So this is a JSON object. You can combine multiple fields in a thing called views. So MongoDB has MongoDB views. Now the data model will be impacted. But now you can create an auto-embedding search index on that view. So what will happen is a composite of plot and title can be used to create that search index. And this way you can iterate on things. With that, let me open it up to any questions. Can you go back to slides, please? Yep. All right, thank you so much. Any questions? Yeah. Yeah, great question. So the question is it English only? So these embedding models are trained on over 80 plus languages. So these are, the search, vector search by definition becomes multilingual and cross-lingual by default. So you can index your documents in English language, search for them in French language. But yeah, we have language-specific benchmarks available for these models as well. But you have almost all the languages present on the internet very well represented in how they work. Yeah, so James, you also want to come over for question and answers?
Sure, hopefully my mic is still working. I think the question was at query time? Are queries embedded once or are they embedded multiple times? So during the query path, the one query is picked up by one MongoT, and then we'll reach out to the embedding service, get the vector embedding, and then send the results back. The system does not cache that vector, however, so if the same query comes in, we will go to the embedding service again to fetch.
Yeah.
But yeah, it's once per query. We'll hit the embedding endpoint.
Yeah. Right. So the question is, if a user asks a similar question, is the query if that vector is cached somewhere? So the answer is no, we don't do that. That's something you can implement yourself. We have some tutorial for something called semantic caching. That's available in our MongoDB's LangChain package, or you can do it off the shelf. But something you will want to implement based on your use case, right? Like, so there is a question of, in a semantic cache, how similar queries are you able to tolerate? So you can do that.
One question, is it multimodal already? It understands images as well, or videos?
Yeah, this is just text. So we have a multimodal model that we announced today in 3.5. But if you go back to the slides, there is a modality parameter right now. So this is text only. In the future, we'll add multimodal options.
We got time for one more question, folks. Sorry.
How many MongoDBs are running at a time, and if one MongoDB goes down, what happens and how?
Yeah, you want to take that question?
I think the question was how many MongoTs are running at one time. That really depends on your deployment. I think the image that I showed represented sort of one MongoT, a one-to-one relationship between MongoD, the database, and MongoT, the search process. But you can actually attach multiple search processes to one instance of the database. So it's really up to you. You figure your cluster, how many replica sets you want, and then how many search processes you want to attach to each replica.
Yeah, so if you're running on Atlas, by default, you will have a replica set of 3. So 3 MongoDBs to make sure there is durability and consistency. And if you enable search, it will be 3 search processes in a couple architecture. Or if you enable search node, that can be 2 to 32. But yeah, this is self-managed, so you can deploy it however you want. All the flexibility is there. With that, thank you so much. Hopefully this was useful. And we are going to be around for a bit. If you have any questions, please come and talk to us. Thank you.